Finding the special values of the Clausen integral function. So basically in this video, we will find some special values of Clausen integral function where the inputs are 0 or pi by 2, 2 pi by 3, some of these standard angles. First of all, you should know that the Clausen integral function is defined as the following sum. Sum from n is equals to 1 to infinity of sine of n theta divided by n square. Yes. Now, there is also an integral representation for this function, and this is a good integral representation, so that's why it's also called the integral function, which is integral from 0 to theta of minus ln of sine x by 2 dx. So this is the integral representation for the Clausen integral function. Okay, if you know this, now we are good to begin our solution. First of all, CL2 of 0 is 0. It's obvious because if you put theta as 0, sine of 0 will just be 0 and sum of zeros will just be 0. Yeah, that's kind of obvious. CL2 of 0 will just be sum from n equals to 1 to infinity of sine of 0 times theta by n square, and sine of 0 is just 0. So that's why sum of zeros, which will obviously be 0. So that's why CL2 of 0 is 0, and the first one is proved. Similarly, sine of pi theta is also 0. We know that the value of sine pi times any constant, sine pi, sine 2 pi, sine 3 pi, all are 0. So that's why if we place pi over here, CL2 of pi theta, that will also be sum of the sum from n equals to 1 to infinity of sine of pi thetas, which are 0. That's why this sum is also 0. We get the second one. Now third one, CL2 of pi by 2. Yes. Now this one is a good one. We know that CL2 of, oh, sorry, I'm sorry for that. Okay, so we have CL and 2 of, let's say we have pi by 2. Now this is sum, I don't know why this is happening now. Okay, sum from n equals to 1 to infinity of sine of pi by 2 times theta by n square. Yes? Is it? Oh, no, sorry, pi by 2 times n, not theta, because theta is pi by 2, now sum pi by 2 times n divided by n square. Okay, so now let's observe the values of pi by 2 times n. So if n is 1, sine of pi by 2 is also 1. Yes. If n is 2, sine of pi is 0. If n is 3, that is minus 1. If n is 4, sine of 2 pi is 0. If n is 5, 1, 6, 0, 7, minus 1, 8, 0. Yes. Now, if you know this fact, now we are good to begin this problem. And now we can rewrite this sum as sum from, let's say, n equals to 0 to infinity in minus 1 to the power n by this is 2n plus 1 square. Yes, you can see that only odd terms will be there. Firstly, only odd terms will be there because for even this goes to 0. Yeah, and for odd term also, now for 1 this is positive 1, for 3 this is negative 1, for 5 positive 1, so that is the same thing. Yes, these two sums are now the same. Now we know that this sum is actually just the Catalan's constant. Yes, 1 by 1 square minus 1 by 3 square plus 1 by 5 square minus 1 by 7 square, and so on. We know that this sum is just the Catalan's constant g. That's why we get this as g. Do you get it? Okay, so this one also proved. Now CL2 of minus pi by 2. Okay, first of all, we know that CL2 function is odd function. Yes, CL2 of minus theta will be sum from n equals to 1 to infinity of sine of n times minus theta, yes, by n square. Now sine of minus n theta, that's an odd function. Since sine is an odd function, we can say that this sum will be equals to minus sine of n theta by n square. Now this minus sign can come out of the sum. So we have minus sum from n equals to 1 to infinity of sine of n theta by n square. Yes. Now this one is just the Clausen integral function, so this is minus CL2 of theta. Okay. You might have noticed that since CL2 of minus theta is minus CL2 of theta, that's why CL2 of theta is an odd function. Now if it's an odd function, now we can easily find out the value of CL2 of minus pi by 2. This will just be minus of CL2 pi by 2, and since CL2 of pi by 2 is g, this is minus c. So that's why we get CL2 of minus pi by 2 as minus c. Now CL2 of 3 pi by 2. For this I can just use the reflection formula of Clausen function. We know that the reflection formula of Clausen function is CL2 of theta minus CL2 of pi minus theta is equal to CL2 of 2 theta by 2. Yes, this is the reflection formula of Clausen function. Yes, yeah, good. Now if I substitute theta is equals to minus pi by 2 over here, what I will get is CL2 of minus pi by 2 minus CL2 of pi minus pi by 2 will be equals to pi plus pi by 2. So CL2 of 3 pi by 2. Yes, and then this is 2 times minus pi by 2. Yes, theta is minus pi by 2. So 2 to cancel. Now CL2 of minus pi, that will just be 0 because that will now be sine of minus pi, and sine of minus pi is just 0. So this whole sum goes to 0. So this is 0. From here we can see that CL2 of minus pi by 2 is actually equal to the CL2 of 3 pi by 2. Yes, and we know that CL2 of minus pi by 2 is minus c. So that's why CL2 of 3 pi by 2 is also minus c. Yes, this is how we get CL2 of 3 pi by 2 as minus c. This is also done. Now 5 of them are done. Now there are two heavy values of CL2 2 pi by 3. This is 120, this is 60. Yes. So let's do it for 2 pi by 3 first, because I have it done in the same way. Now, to find the CL2 of 2 pi by 3, we will use a second integral representation of CL2 function that I just introduced in the previous video, which I will link in comment as well as the link over here. This is just the previous video in my channel, which is live before this. Okay. Now for that we will use the integral representation that we just derived in previous video, which is minus sine theta integral from 0 to 1 log x divided by x square minus 2 cos theta x plus 1 and then dx. Okay, so we have this. We want to find CL2 of 2 pi by 3. Okay, we know that sine of 2 pi by 3 is root 3 by 2. Yes, an integral from 0 to 1 log x, and then cos of 2 pi by 3 is minus 1 by 2. So x square minus minus plus 2 and 1 by 2 will be 1. So x square plus x plus 1 dx. Okay. Now we have all like I have dealt a lot in my channel with such kind of denominators, where we just multiply it by 1 minus x, and this becomes a minus b, a square plus a plus b square, which comes to be a cube minus b cube. I have done such integrals, so I just remember, yeah, this is just a technique that we have been using quite a lot. So CL2 of 2 pi by 3 will be equals to minus root 3 by 2. Yes, now integral goes from 0 to 1 log x times 1 minus x, and this is 1 minus x cube dx. Now let's make a substitution that y is equals to x cube, and this is because like such integrals, integral from 0 to 1 log x and then x to the power p by 1 minus x dx. We have done such integrals by dealing with the poly gamma functions, yes, or digamma function. This integral can be solved from digamma function, so that's why I'm trying to take it to the same form. Eh? Okay, now so I have made the substitution, so we get CL2 of 2 pi by 3 as minus root 3 by 2. Yes, then integral will be again from 0 to 1 itself. If you just cube it, Now x is y to the power 1 by 3. So log of y to the power 1 by 3, 1 minus, again x is y to the power 1 by 3 divided by x cube is y, so 1 minus y. Now x is y to the power 1 by 3, yes, so that's why dx will be 1 by 3 y to the power minus 2 by 3 dy. Yes, now this answer also comes in front because we are taking log, so we have 1 by 9 in front. CL2 of 2 pi by 3 comes out to be minus root 3 by 2 times 1 by 9 integral from 0 to 1 log of y. Yes, if you multiply y to the power minus 2 by 3, this will be y to the power minus 2 by 3 minus 1 by 3, and minus 2 by 3 will be y to the power minus 1 by 3. So y to the power minus 1 by 3 divided by 1 minus y dy. Yes, 1 by 3 and 1 by 3 only 1 by 9. Okay, good, looks good. Now after this, to solve this, now let me just simplify it. Okay, there's nothing to simplify actually. To solve it, now let me show you something. The Tie logarithm integrals. We know that first of all the Tie gamma function is, sorry, again I mean the integral for Tie gamma. Okay, first of all we know that the Tie gamma function is defined as negative of polynomial constants plus the xth harmonic number. Yes, and now you can write the xth harmonic number as integral from 0 to 1 of 1 minus t to the power x by 1 minus t dt. Yes, now if I take its derivative of the digamma function, now I get trigamma function. This will go to 0, and over here we will have integral from 0 to 1 minus t to the power x times ln of t 1 minus t dt. Yes, so you see that this integral from 0 to 1 of t to the power x times ln of t by 1 minus t dt, this integral is just equals to the negative of the trigamma function of 1 plus x. Do you see this? Do you notice this? Yes, I guess so. Now, if we know this thing, now it will be easier. Yeah. Now we can solve this because now we can break into two integrals. Yes, and then I can say that CL2 of 2 pi by 3. Now this is, if I cancel with root 3, this will be root 3. So minus 1 by 6 root 3. Yes, and now this is just minus trigamma of this times plus 1 is 1 by 3. Yes, and then again we have minus and again minus, so plus trigamma of this plus 1 is 2 by 3. So this is our answer. Yes, and now I have to write it properly. CL2 of 2 pi by 3 can be written as minus 1 by 6 root 3. Yes, trigamma of 2 by 3 minus trigamma of 1 by 3, and this is the required result. So let us see if it's correct or not. CL2 of 2 pi by 3 is minus 1 by 6 root 3 trigamma of 2 by 3 minus trigamma of 1 by 3. Okay, yes, it's good. So that's good. Now the next one, last one. Okay, so now we need to find, I hope you get this. Yes, over here it was just using this integral representation, then making it 1 minus x cube, and then use substitution and the trigamma integral. Yes. Now next one, CL2 of pi by 3. This is slightly different. Yes, it also comes in terms of trigamma function, but it's slightly different. Now when we want to find trigamma of pi by 3, again we do the same integral representation. So we will have minus sine of pi by 3, and then integral from 0 to 1 of log x, yes, x square minus 2 cos pi by 3 times x plus 1 dx. Okay, looks good. Yes. Now this is minus sine of 60 is root 3 by 2. So minus root 3 by 2. Yes, and then integral from 0 to 1 log x, and cos 60 is 1 by 2, so this is just x square minus x plus 1 dx. Now I can multiply this by x plus 1, because if I do this, this will just be a plus b, a square minus ab plus b square. We know that this is x cube plus 1 cube. Just like in the previous one, we are trying to simplify the expression in the denominator. Minus root 3 by 2 integral from 0 to 1 log x, and then x plus 1, and now this is 1 plus x cube dx. Okay, now I make a new substitution. That y is equals to x cube. Yes, if we make this substitution, this will be minus root 3 by 2 integral from 0 to 1, and y to the power 1 by 3 is 1 by 3 log of y, and again x is y to the power 1 by 3 plus 1 by 1 plus y, x is y to the power by 3, so 1 by 3 y to the power minus 2 by 3 dy. Now 1 by 3 and 1 by 3 is 1 by 9, and that comes out, so we have minus root 3 by 2 times 1 by 9 integral from 0 to 1 log of y, and this 2 will be y to the power minus 1 by 3 plus y to the power minus 2 by 3 by 1 plus y dy. Now previously we had a standard integral involving y 1 minus y, but for 1 plus y there is in fact a beta function integral, but for that we need to have the limits of integral from 0 to infinity, which we don't have. So in this case we will try to use the geometric sum formula, because y is from 0 to 1, so that's why we can change this geometric series, but the ratio is minus y. So let's do that. Now this is minus 1 by root 3 and 9 cancel out to give 3 root 3, so this is minus 1 by 6 root 3, an integral from 0 to 1. Yes, and now log y. Yes, good. And then y to the power minus 1 by 3 plus y to the power minus 2 by 3, and 1 by y. This can be written as sum from n equals to 0 to infinity minus y to the power n dy. Yes, you can write it like this. Now if we change the sum and integral, we have minus 1 by 6 root 3, and then sum from n equals to 0 to infinity integral from 0 to 1. Yes, and then we have minus 1 to the power n log of y, and y to the power n minus 1 by 3, similarly plus minus 1 to the power n log of y, y to the power n minus 2 by 3 dy. Yes, is that good? Yes, it looks good. This dy is for eh? Now I guess you know about these integrals of log n powers of x. That is also some gamma function integral. We know that integral from 0 to 1 of log x to the power p x to the power q dx. This integral will just be minus 1 to the power p gamma of p plus 1 divided by q plus 1 to the power p plus 1. This is the integral of the gamma function, where e has been changed to log. Now if we use that property, 1 by 6 root 3, yes, and then sum from n equals to 0 to infinity. Over here minus 1 to the power n as it is, yes, and then again we will have minus 1 to the power 1 gamma of 2 by n plus 2 by 3 whole square. Yes, similarly over here also minus 1 to the power n, and then minus 1 to the power 1 gamma 2 by n plus 1 by 3 whole square. So this is the solution of these integrals. Now we have to sum them, but since there are alternating powers, it looks like that can be difficult for us. Yes, so over here we have sum from n equals to 0 to infinity, and then minus 1 to the power n plus 1 gamma of 2 is just 1 by n plus 2 by 3 square. Yes, and over here this is minus 1 to the power n plus 1 gamma of 2 is just 1 divided by n plus 1 by 3 square. Yes. Now what we can do is break these alternating powers into two sums. How? The Okay, here's how. Now when n is even, this one is negative number. Yeah, minus 1 has the power of negative number, so that minus 1 to the power negative number is just minus 1. So we can say that for even powers this is just minus 1. So that means when for every n, 2n is the even number. Yes. And similarly for this same sum, when we have n as odd, that is positive 1, and odd number can be written as 2n plus 1. So I'm basically breaking this into all even terms and all odd terms. Yes, square. Same over here also. Sum from n equals to 0 to infinity minus 1 by 2n plus 1 by 3 square. Yes, again plus sum from n equals to 1 to infinity plus 1 by 2n plus 1 by 3 square. So this is it. Now minus 1 by 6 root 3. Yes, minus 1 by 6 root 3. And then this can be written as, okay, now first of all I can take 1 by 4 common first. I can take first 1 by 4 common. Let me do that first. Let me take 1 by 4 common first. So that over here I have minus 1 by 24 root 3. 24 root 3. After that we will have sum from n equals to 0 to infinity minus 1 by n plus 1 by 3 square. Yes. And then plus sum from n equals to 0 to infinity plus 1 by n plus 1 plus 2 by 3 is 5 by 3, so 5 by 6. 5 by 6 square. Again, sum from n equals to 0 to infinity minus 1 by n plus 1 by 6 square, and then plus sum from n equals to 0 to infinity 1 by 3 plus 1 is 4 by 3, so 2 by 3, n plus 2 by 3 square. Yes. Now I can write these sums in terms of polygamma functions. I guess you know that. No, okay, wait. Do I really need polygamma function right now? I guess I need them. Now polygamma function is, over here we had seen the trigamma function, digamma function. Yes. Now similarly we know that we can write digamma function as minus of Masonic constant plus the sum representation for harmonic function is sum from n equals to 1 to infinity of 1 by n minus 1 by n plus x. Yes. Now if I differentiate this, digamma dance of 1 plus x will just be, this will go to 0. Now sum from n equals to 1 to infinity. Yes. And then this will go to 1 by n plus x square. Yes. Now if you reduce this x by 1, over here if I put x minus 1, I can also make that n minus 1 and make n go from 0. So I can say that digamma dance of x will be equals to sum from n equals to 0 to infinity of 1 by n plus x whole square. Yes. So this is just digamma dance of x. Notice that when n goes from 0 to infinity, n plus x square is just digamma dance of x. So we'll use that over here. Yes, all of them go from 0 to infinity. So that's why I can say that minus 1 by 24 root 3. Now this is minus digamma dance of 1 by 3 plus digamma dance of 5 by 6 minus digamma dance of 1 by 6 plus digamma dance of 2 by 3. And this is our answer. Let's check the answer. Minus 1 by 24 root 3 minus digamma dance 1 by 6 minus digamma dance 1 by 3, yes, plus digamma dance 5 by 6 and plus digamma dance 2 by 3. Yes, that is exactly what we have over here, and we have found the value of the Clausen integral function of pi by 3. So we have found all these values, and I guess our mission is now accomplished. I hope you enjoyed the solution and hope these values are helpful for you, even if you are working on some scientific papers, any other engineering stuff, or anywhere you are working on. Hope that these values are helpful and this video helped you. Thanks for watching. Look forward to seeing you again soon. Have a good day.